These are our findings from FOMO number 1, inelastic 2D collisions. So the overarching objective of our lab was to determine the bounciness of a ball. To do so, we examined how the percentage of kinetic energy lost in a 2D collision is impacted as velocity changes. Our experiment focused on bouncing balls at both fast and slow velocities and calculating the initial and final kinetic energies.
So the models and ideas that we're using for this experiment helped shape our prediction. Our prediction is that the ball with the greater initial velocity will lose a greater percentage of kinetic energy, and this is related to the momentum principle and conservation of momentum. The collision that is taking place is an inelastic collision, which means that kinetic energy is not conserved. And because the mass is constant, we know that in order for momentum to be conserved, the velocity must change. We know that momentum is conserved because of the law of conservation of momentum and by defining our system as the ball and the floor. If our system were just defined as the ball, momentum would not be conserved and we could not apply these ideas.
Alright, so for our experiment, we took and bounced a ball off of the floor with slow and fast velocities. The mass of the ball was the same, 88.7 grams in each run of the experiment, and the height was kept constant at 1.1 meters, and the distance was kept constant at 1.2 meters, and from this we can conclude that the angle that the ball was released from is also constant. We used AutoTracker to analyze the velocity of the ball before and after contact with the floor, and this was done to help minimize any errors in tracking. From the final and initial velocities and the mass of the ball, we were able to solve for the kinetic energy before and after the collisions of both balls.
Using AutoTracker, we were able to obtain an initial velocity value of 10.2 meters per second and a final velocity value of 6.246 meters per second. The initial velocity value was obtained just before the ball collided with the ground, and the final velocity was obtained just after the collision with the ground. Plugging into the equation 1/2 times mass times velocity squared, we were able to obtain an initial kinetic energy of 4.61 joules. Using the same equation, we were able to calculate a final kinetic energy of 1.73 joules. Plugging into the equation the initial kinetic energy minus the final kinetic energy over the initial kinetic energy, we were able to obtain a value of 62.5% kinetic energy loss.
And for our slow ball collision, AutoTracker gave us an initial value for velocity of 9.05 meters per second and a final velocity value of 7.59 meters per second. And again, these values were obtained just before and just after the collision. Using the kinetic energy equation, 1/2 times mass times velocity squared, we were able to calculate an initial kinetic energy for the slow ball of 3.63 joules and a final kinetic energy of 2.55 joules. Using the same percentage loss equation, we are able to calculate that the slow ball lost 29.7% of its kinetic energy in its collision with the floor.
We believe that we got the results that we did because when you have a greater velocity, there will be a greater impulse because it has more momentum when it strikes the ground. Because the mass is held constant, the greater impulse in the ball means the greater change in velocity, which also translates to a greater change in kinetic energy. But there is some error in this. It is difficult to hold the distances and thus the angle completely constant due to human error, and it's difficult to throw the ball exactly at the same spot for both runs of the experiment. Overall, though, our results reflect the definition of inelastic collisions and the law of conservation of momentum.